All right, I think we're ready. Today, mostly what we'll do is review, like go back over some problems, work over some examples of things that will be on exam one. If your exam one is Thursday, if you're not sure what it would be on exam one, here, if you go to, let's see, if you go to exam one, June 24th, there is a summer 20, and again, well, let's go ahead and fix that. Let's make it say 2021 so that it's up to date. So summer 2021 exam outline. Now when you open this, it's actually going to say 2014 on it, but it's fine. And it will have this in there. So the way this exam is set up is these 10 points of content questions or fill in the blank short answer type things. There will be one zero force members. There will be a truss of some sort with loads all on it and many members, and you will be assigned the job of identifying the zero force members in that truss. And you just write down member AB is a zero force member, you know, so forth. And stress strain graph, this is a plot you will need to create that labels. You need to draw a stress strain plot, or a representative one. That doesn't have to be super accurate, but a representative stress strain plot of a ductile metal, and label some points on it. So I'll want to know maybe the ultimate strength, or the strain at fracture, or the modulus of elasticity. You know, some of the different material properties that you can get from the stress strain plot. You'll need to label them. Stress, that just means some content question about the idea of stress. Remember, axial stress is the force over the area that the force is applied to. It's defined as the intensity of internal forces. Strain is the severity of deformation. And so I guess that's strain and not necessarily stress, but it's related to stress. So there'll be some question or two that have you answer content questions about stress. Same thing with equilibrium. You'll need to answer some content question about equilibrium. And then there are 1, 2, 3, 4, 5, 6, 7, 8. It looks like 8 questions that have to do with the one-step type, maybe 1 or 2-step type problems. I mean, you've got resultants, 2D equilibrium, all of these relatively straightforward, like the quiz level of questions for these topics that we've talked about. Centroids is in there. That's the most recent topic that will be on the exam. Moments, so that's just literally calculating a moment of a force about some given point. And then they step up. There's 5 questions that have more than one step to them. So this is method of joints, method of sections. You're not going to be told to solve this truss using method of joints or sections, but one method will be superior to the others as far as time, you know, how long it takes to solve it with one method versus the other. And then there's a couple, 3 advanced above average questions. So these are the ones that in order to make an A, you're going to have to probably put more time into these to get them right compared to the others. So this is out there. And I thought today, if I don't get any particular questions about problems to actually go through, I have 2 in mind so far, but if you have one, particularly a web workroom, that way we can all look at it together, then let me know, send it over in the chat. But I have 2 already that I plan on doing. One of them is work through this truss, and another one is an axial deformation. I think there's one that has a screw shape, and it's doing a couple of different things. One of them is axial deformation. And so those 2, well, I got to find that other one. I don't remember where it exactly is, but they're both web work problems. And so I've had questions mostly about those 2. So I thought they would be good ones, or this one and the other one would be good ones to kind of work through. So why don't we just start with that? And again, if you have a particular one that you're interested in, we should have plenty of time to do some others also. So put it in the chat and we will look at that. So here I'm just copying it. Let's go over here, paste this thing, And this one is definitely something that I would expect to possibly be on a exam question. Now, an exam question isn't going to ask you for 3 different things, but it could ask you for one of these for sure. Or it could ask you for a thing related to one of these. So the stress in member DE, or the axial change in length of member AM, you know, something like that. All right, so on this problem, what I would do is first I would look and probably go through and mark somehow the pieces I need. So I need AM, I need that piece, DE, and IJ. So they're not really, this particular problem isn't set up in a way that makes it obvious that there's a single section I could draw that solves everything, because these are scattered around. It still could be something useful to do, method of sections, but let's keep going with it. The next thing I would probably do is look for zero force members. So zero force members that I can see would be this piece, IJ, which would also make IE a zero force member. I'm just going to kind of erase them. EJ would be a zero force member. There's 2 collinear, no force at J. That third one is a zero force member. That actually helps us solving this IJ in a second. Here, I've got DE and EG collinear, no force at E, so this is actually a zero force member. Here, I lost my cursor. There we go. BM would be, BL would be, CL would be, DL would be, and so look at that. Everything on the inside of this one ends up being a zero force member. Now that's not any of the ones I'm trying to solve for, but it does simplify our free body diagrams that we have to do. I don't know if I specifically said this when we were talking about zero force members or not, but when you do find one, those 2 collinear members have the same force and same sense. So they're both tension, both compression, whatever it is. So same magnitude, same sense. So now knowing that IJ has the same force as JK or HI, then that kind of helps me solve some of these. In fact, I could do something pretty straightforward. Now, it's not symmetric. The loading is not symmetric because the loading is angled. So it's not as simple as like one half of the truss is a mirror image of the other half. So that's not as simple as it would be. But we could do this. First, it looks like we're going to need to find our external reactions. So let's go over here and kind of draw what we have for a truss now. We have more or less that. There's a pin reaction at A. We'll call it AY. There's a roller reaction at A. A pin reaction at H. So we'll have HY and HX, which is not 0 this time because our force F, 2.1 kips, is not vertical. It's at an angle of 16 degrees from vertical. So there is an X component that has to be reacted. So let's work on finding those. It looks like we have dimensions that would say this is 12.4 feet, and this distance is 3 A's. So let's see what that is. 8.3 is A for me. 8.3 times 3 is 24.9 feet. And then this is another 3A to get to this end. All right. Let's do what I would normally do and do summation of moments. Actually, let's move this thing so we can write around it. Let's move it down here. Somewhere down there. What I would normally do once I get to this point for solving external reactions is I would probably do summation of moments about the pin. So I would do that just because the pin has the two unknowns, hx and hy, and by summing moments about that point, I don't have to try and solve those. I'll end up being able to solve for ay. I'll just make clockwise positive. That just works better in my mind, but you can do whatever you want. So I have ay times its moment arm of, there's two 24.9s, 49.8 feet. And it's going around clockwise. The 2.1 kips is at an angle. So how I would handle that is I would create two components for it. The vertical component would be 2.1 times cosine of 16. So 2.019 kips. And the horizontal component would be 2.1 times sine of 16, 0.579 kips. If you're using vectors and things like that, you don't have to break them into x and y components, but in this course we're going to do everything in terms of x and y components. So I need x and y components to write this moment equation. So the x component, the 0.579, it's going around clockwise, so that's plus 0.579 kips, and has a moment arm of 12.4 feet. Where would this problem fall on the exam outline? This problem, well, first of all, it would only be a piece, right? You would either be solving for AM, DE, or IJ. And so it wouldn't be this above average one. Right now I don't have an average one listed as a oh no, I do. I have method of joints, method of sections. It would probably be one of these two, the average level. So it's multiple steps. It's made a lot simpler if you can find the zero force members. The one here at the fundamental question level probably doesn't have you find reactions, and it's probably, you draw one method of joint somewhere and solve the truss piece that you're interested in. I would say this is average level, but it's a little bit, on the tough average side. And you would only be solving one of these things. You wouldn't solve for AM, DE, and IJ. It would only be one of them. Actually, a good question of where this fits on my levels. This is slightly tough average problem. So if I put this one on as one of the average, or something like this as an average one, the other average one would probably give you a little bit more straightforward solution process, because this one does have you do a few extra steps. And if you don't see the zero force members, it's not any harder, except that now it looks more intimidating. All right. We need to do the vertical component, writing our moments about H. It's going around counterclockwise, so I'm going to put minus on it for my sense. I said positive was clockwise. Why is the x and y component of the force not negative? They are, but what I'm writing, and if I was writing a summation of forces, then I would need negative and positive signs, because they're going left and going down, which, I didn't draw it on here, but normally x is positive when it goes right, y is positive when it goes up. But since I'm writing summation of moments, the positive and negative is determined by the sense of the moment, not the direction of the force. And so these two components, one of them is actually creating a clockwise moment about point H. The x component actually would create a clockwise moment about point H. And the vertical piece, the y component, creates a negative counterclockwise moment. And so that's where this negative sign is coming from. And the direction I drew them is because I was given, like in the problem, it does give me the direction for the force F. And so for that direction force, it goes down and to the left. then the components of it have to go down and to the left. So that's how that I chose which way to draw the components in the first place. This one, this 2.019 kips, has a moment arm of 24.9 feet. And that's it. There's no other forces. HX and HY, both line of action for HX goes right through point H. This is point H, in case we were confused. And so it doesn't create a moment about H. HY, line of action goes through point H. I'm not drawing the lines of action on here, but there would be the line of action for HY. It would also go extend this way. HX would go out this way and to the left. And those lines of actions actually go through point H, which is like trying to open a door by pushing on the hinges, not on the door handle. And the door doesn't swing when you push on the hinges, the point of rotation. Now, that's a thing that a lot of people get confused about, is they think this H, moments about H, they think that is, we chose it because that is a pin, or because it is the point of rotation. But that's not really what this equation is telling you. This equation is saying pick any point. A point that's not even on the truss, a point that we didn't draw, whatever. And as long as the truss, the body of the truss, is not rotating about that point, whatever it is, then this equation has to be true. So the summation of moments about H, I only picked H because by picking H first, I eliminate these two variables in my equation. So instead of writing an equation that has three unknowns in it, AY, HX, and HY, I don't have HX and HY in that equation, in the equation I'm writing now. And so I can actually solve the equation. There's only one unknown in there, and it's AY. If I had chosen some other point, like if I chose this point, that'd be really bad because all I'd have were unknowns. I would have AY, HY, and HX all show up in the equation trying to create moments about this point. I don't even know what that letter is. And I wouldn't have any known values. So there is a strategy on which point to pick, but you can pick any point that you want. And at this point, we can solve this equation that I just wrote because the only unknown in there is AY. And that's why I chose to do summation of moments about point H, because I knew that there would only be one unknown. I'd have some things that I did know, and I should be able to solve for it. So let's see if we get, well, we won't know if we get this right. Let's just see what it is. So I've got 0.579 times 12.4. My units are going to end up in kips, right? Because I've got feet and kips all mixed together here. All the distances are in feet, and all the forces will be in kips, even though it looks like I didn't write some of them and I mixed up my symbols some. But it's fine. All right. Minus 2.019 times 24.9. Okay. So I get AY equals, I'll move that minus to the other side of the equal sign, but so it becomes positive. 43, that's kip feet. And then I need to divide by the 49.8 feet. And I get AY as 0.865 feet, kips. So 865 pounds. That seems reasonable. Seems reasonable. So we'll go with that. At that point, I can go and write one of my other two equilibrium equations. So I could write summation of forces in the y direction. And I've got AY plus HY minus the 2.019 kips, so just the y component of the 2.1 kip external force. And I just found a value for AY. So that would tell me HY equals, I move the 2.09 to the other side of the equals, it becomes positive. Then it needs to subtract off the 0.865. and I get 1.154 kips. And then I could have done this from the beginning, but I could do summation of forces in the x equals 0. And I have, the way I drew the hx component is to the left, so I actually have negative hx minus the 0.579 kips. This is kind of where your question was, that they are negative when I'm writing equations that talk about x and y directions. But when I'm talking about moment directions, it's the sense of the moment that determines if it's positive or negative, not the direction of the force. All right. So this would just say that hx equals negative 0.579 kips. And this negative sign means that I drew the hx arrow in the wrong direction. Whoops. When I drew it, you know, way up here. So I just picked a direction. I could have drawn it to the other way, but for whatever reason, I drew it going to the left. And clearly, if you look at the free body diagram, I have two x components, hx and the x component of the 2.1, and I have them both pointing to the left. And so one of them has to be going the other way, or else it can't balance. And the 0.579 has to go to the left because it is the x component of the 2.1 external force, which is going to the left. So the component of that 2.1 has to also go to the left, which is why I get a negative value for hx. So I've got my three external forces here. I've got ay, hy, and hx. So I've got those. And again, depending on what I was actually solving for, I may not need all of these. For instance, if I were just solving for AM, which is this piece, if I were just solving for that, all I need is AY. I don't need HX and HY. I could just do method of joints at A once I get AY. So some of these problems are set up so that you don't necessarily... I'm going to say you don't have to solve every piece of the truss in order to answer a test question. There are going to be homework questions where you do that, but a test question is probably set up in a way that you're not going to need to solve everything to get to that problem, just because it's going to take an inordinate amount of time to do. All right, so at this point, why don't we try and find the tension in AM, recognizing that they mean tension as a positive number and compression as a negative. So it could be that the tension in AM is actually a negative number, meaning it's a compression. So AM was originally right here. And at this point, I have a value for AY. So I think method of joints at A is our best bet. So we'll draw a dot for A. We'll put AY on here. And we solved it to be 0.865 kip. We will draw AM. I'll draw it in tension, meaning that that arrow goes away from my free body. And then I'll also draw this other one in tension, just because I don't know, and it's labeled AB. We need something about the angle of AM. And it looks like we have the rise for that whole piece, AM, ML, L, K, it looks like. That whole piece has a rise of B and a run of 3A. So we will use that. I probably need to move some stuff around. Put that over there. So, you know, if I extend this out so that we can put a triangle on it. A rise of B, which for me was 12.4. A run of 3A, 24.9. And that will give us a hypotenuse if we do 12.4 squared plus 24.9 squared. Square root of that, 27.82. Now, I am rounding a lot in web work. You know how it's very picky on rounding. On the exams, it is not as picky. All right, so at this point, if I'm trying to find for AM, it looks like if I do the summation of forces in the y direction on this free body diagram, I'll have the value for AM, and I won't even have to worry with AB. So I'm going to do, based on this free body diagram, summation of forces in the y direction equals 0, because I know point A, the joint, the physical joint at A, or pin at A, is not moving up and down. So we have plus, again, x is positive horizontally to the right, y is positive vertically up. All right, so that means 0.865 kips, that's the reaction at A, minus TAM times, I only want the y component, so 12.4 over 27.82. Okay? Or you could go find the angle that TAM is at, and do the actual sine or cosine of that angle, depending on what angle you actually measured. All right, these have to add to 0, and the only unknown in there is AM. So TAM equals, let's see, 0.865 divided by 12.4 over 27.82, 1.941 kips of, and that it came out positive. I drew the arrow as a tensile arrow, so that should mean it's in tension. Let's see if web work agrees with us. $1940.88. We put 1941 because I rounded. If I didn't round, I would have had 1940.7. So maybe web work would have not liked that. It'd have been fine on the exam. The exams are more coarse versus the the precision that web work expects. And we rounded several. We rounded in the calculation of all of these reactions, and we rounded in these force components, and we rounded here. So there were several stages of rounding that compounded each other, but I would still say that's the correct answer. Let's see. The rest of this, so that would be, if this were a test question, one of those average level questions, what it would be, or a way to present it would be, find the tensile force, or find the force in member AM, and what I would do at that point is I would look for these zero force members, find out that, oh, everything's a zero force member. All I need is the reaction at AY, which I could get with this one equation. So I'd write that one equation, and then I would draw this free body diagram to do method of joints at A, and write this equation. So there'd be the two equations you'd write and two free body diagrams if you needed to draw the free body diagrams. On the exams, there are many problems where there's no partial credit, but it is still better to write out your work. You'll be given a chance to upload your written work, and just in case that there's something happens or whatever, I can go back and look at your written work. Maybe it's a multiple choice, and all your written work supports one answer, but you accidentally clicked another answer. Then your written work can show that, oh no, you just clicked it wrong somehow. So it is best to write out as your work as clearly as you can. You'll scan it in or take a picture of it or whatever, and upload that once you're done with the exam, and that will be better. You don't have to spend inordinate amounts of time making it super neat, just because you don't have a lot of extra time on the exam, but you have enough time to write it down. And if you're going to write it down in a readable way, so that I can give you credit if you somehow missed the problem but actually got it right on paper. So this web work problem actually wants us to do DE and IJ also. So in that case, what I would end up doing is I would do method of joints at H. So I would just look and see that, well, DE, actually, DE, you already know if you finish doing this one. Because AB across the top here, once you eliminate all of these internal pieces as being zero force members, then this entire row has the same force, same magnitude, and same sense. So it's all compression at whatever force AB is. AB equals BC equals CD equals DE equals EJ equals, or EG equals GH. I don't know why the G's in the weird order like that. It's kind of weird. Oh, they didn't put F because F is the force. Okay, that's why. Just to not confuse it. All right. So, but if I hadn't done that, then what I would do is go to joint H, which I'll need anyway because IJ does not equal AM. You know, this truss is symmetric geometry-wise, but the external force is not symmetric, and so the reactions aren't symmetric. So you couldn't just say that AM is the same thing as IJ. It is a different value. And it'd be simplest to do method of joints at H to get that. In my imagination, it would be simplest to do that. There are other ways to do it, but that's the simplest. All right. The other problem I wanted to work on, if I can find it, I'm not sure why that... Oh, that's MathCAD. Yeah, we don't need MathCAD right now. The other one I wanted to work on had to do with axial change in length, if I can find it. Oh, wait, we didn't do homework 6. Homework 6 we'll do later. It is more moment oriented, and we didn't do that specifically yet. Let's see. So this problem, both of these, you know, this one is axial deformation. On our outline, there's one at the fundamental level and one at the average level. This one is certainly the fundamental. It's definitely not the average level, and it might be a little simple. The only thing that makes this one a little bit more than just a straightforward one is it's actually also asking for factors of safety and stress and things like that. So that makes it maybe a average level one or fundamental, but it's pretty straightforward. This one has two different shapes and, you know, I think probably even two different materials. Yeah, two different modulus of elasticity. Now on the exams, you won't always be given the modulus of elasticity like you are here. You might have to go look it up in one of the reference sheets, which you will have access to. In fact, let me show you. You will have access to these in this reference materials folder. You can look at any of these reference, and there's exam reference 1 and 2. That's not exam 1 and 2, that's just two different packets. And in these reference materials, you'll have your material properties and a lot of stuff that you don't need yet. You know, it may not make sense yet, but there's a lot of material embedded in these two references that you can use during the exam. So all of that stuff. All right, so this one is probably average level. This one also kind of average level. Average, it's the same thing. There's just more of the pieces is all. This is the one I think that is giving people the most problem. One of those, I don't know which one. That one, this one is a little more advanced thinking here because you have some overlapping compression and extension, you know, stretching. So let's see which one of these I want to do. I think either this one or this one give people the most problem. This problem 6 looks to be a little bit more involved. So let's work on it some. All right, it's asking us for a bunch of change in lengths. I don't know if we'll solve all of them or not, but we'll do some of it. And it has a bunch of assumptions that we can walk through. All right, there's our problem. So this is a bolt. It's kind of idealized. It's a very thin thread and a thick shank compared to what a bolt would normally be. But it's a shoulder bolt. The shoulder means that part of it is not threaded, the part that's called the shank. The head of the shoulder bolt is a regular hexagon, and it measures 16 millimeters across opposite flats. What that is giving you is you end up needing to calculate the compression of the head itself. There's a force, for whatever reason, there's a force pushing down on the top of the bolt head at FA. And so we need to figure out how the compression of the bolt head, how much that is. So that's why it gives you some dimensions of it. The other dimensions are given below, as well as the forces to which the components are subjected. We want to find the change in length of each segment. Centroids will be on the test. There's a question, will centroids be on the test as well? Yes, they will be. I think there's two centroid problems. One that's pretty straightforward, maybe two pieces you put together, and another one that has 3 or 4 pieces. Some of them are negative, like they're holes, things like that. And we can do a centroid problem in a second too. We should have time. All right, so this is just pure change in length, axial deformation. And the tricky part is that there are, all these different areas and these weird cross-sectional areas. It's got some assumptions. Bearing stress between threads of the bolt and the nut may be neglected. So if you were actually tightening the bolt down, this nut would be stretching out the threads inside the nut. So we're ignoring that. We're ignoring stress concentration effects. So how we have these threads, they're really sharp, and they have sharp roots and sharp tips. And so that's going to be stress risers that would increase the effect of the force applied to them. The force that the nut applies may be treated as a concentrated force. So you see FD over here, it's shown as 2 different arrows, but you can treat that as a single force. You don't have to try and do 2 different arrows. The nut is rigid, so we don't have to worry about the nut compressing or anything like that. The forces applied to the nut and the shoulders of the bolt are distributed evenly. So same thing where they show 2 different forces, but they kind of have this brace that is connecting those forces. In the FA, they actually go in and show it as a distributed force that has the arrows connected together. So there's a little bit of just guidance on how to treat these arrows if they're 2 separate forces or a single force. And these are meant to be a single force instead of 2 separate arrows, 2 separate forces. All right, so, well, let's see. Let's take and let's just start with drawing a free body diagram. Let's not worry with the head of this thing right now. Calculating the area of this hexagon, what I would do is I would just go find a hexagon calculator to figure out the area. The oddness of it is that it's 16 millimeters across opposite flats, which is actually maybe that is not how you calculate. Like if you look up the area of a hexagon, that's usually not what they ask for. See, they're looking for the length of a side, which is actually not what you have. You have the distance across the flats. Let's see if there's a... I'm sure there is some online calculator. Again, most of these are the sides. All right, we got all kind of pop-ups. Let's see if we just put in... No, none of these are... Oh, look, there we go. Side to side, that would be the what we have, the one called side to side here. And ours was 16 millimeters. So our area would be 221.7025 square millimeters. So this sort of thing, some oddball area that you don't have memorized, that's not the kind of stuff that's going to be on the exam, just because it's, having 6 different ways to calculate hexagon area is not something I expect you to walk around knowing. It's fine if you do, but I don't expect you on an exam to know all these things. Area of a circle, area of a square, triangle, yes, but not of a hexagon in a particular way when there's 6 different ways to do it. All right. So our area, I guess we could start with that now that we have the area. Area of the hexagon for us was 221 point something. 7025 square millimeters. And maybe that's an easy one to start with. So I would cut the head in half because that's one section. I have to treat it as its own section because there are forces that get applied to the back of it. It changes area from the head to the shank. It's all the same material, I assume. In fact, I don't know. Oh, it's hot rolled mono, so that's an oddball material that we'll have to look up. I don't offhand know its modulus of elasticity. So if I draw this little cross section or this free body diagram of the head, I cut it open and it's got force FA applied to it. I'm just going to draw FA as a single arrow, even though they drew it spread out. They're just trying to say that it's not concentrated at a single point. And FA is 35.4 kilonewtons. And so therefore the internal force in this section, we'll call this section 1, has to also equal 35.4 kilonewtons. The arrow is pointing towards the body, so this is a compressive force. The head is actually shrinking, so that's technically a negative force. Not negative because it's pointing left, negative because it is compression and pointing towards the body, the free body I drew. So delta for the head equals F of the head, or we called it F1, times L1 over E1 A1. So F1 is negative 35,400 newtons. The length of the head is lowercase a, 11 millimeters. I'm going to have some units I have to take care of in here, it looks like. E is hot rolled mono, so I don't know that. Do we still have, yeah, we still have these. Let's see if I can find it in here somewhere. These are the KSI units, so this will work, but we need to rotate it. Not that way. There we go. There's megapascals. We need these units. So everything else was in millimeters, so we need those. Let's zoom in some on it so we can get a chance at seeing this thing. Hot rolled mono, it's also wrought on here, but that's the same thing. 180 gigapascals. 180 gigapascals is our modulus of elasticity. So that's 180 times 10 to the 9th pascals, which are newtons per meter squared. So these millimeters are messing me up right now. I have more millimeters here in the area. 221.7025 millimeters squared. So I have millimeters once in the numerator and twice in the denominator, so that's not going to work. We'll need to convert those just to avoid getting confused. Why don't we convert both of them? So this is 1,000, well, 1 meter is 1,000 millimeters. Be careful converting the area because I have millimeters squared. So 1 meter is 1,000 millimeters, but I need to square that so that I actually end up with canceling out millimeters squared. I can't cancel out millimeters squared with just 1 over millimeter. So I need to square the conversion factor also. All right, looks like we have all of the stuff in there that we can calculate how much the bolt head got squished. So 221.7025, we need to divide that by 1,000 twice. Multiply times 180 times 10 to the 9th, so 9 zeros there. 35,400. Don't forget that that was in kilonewtons, and so I'll switch it over to newtons. Times 11 divided by 1,000 to get the 11 millimeters to meters. And then divide all of that by our denominator. And I get a super tiny number in meters. 9.758 times 10 to the negative 6 meters. It's probably wanting us to put these answers in millimeters, I assume. Well, it actually doesn't even say. So it just says delta, so we can put them in whatever we want, as long as we put the units in there. Section AB, that's this first one. So it wanted negative, and then 0.123459758 meters. See if we're anywhere near what it's wanting. Oops, I don't want to show the correct answers there. Hey, we got it right. They had it in millimeters for their default answer. We just put it in meters. So that, just doing the one, that would be actually a basic one, except for the fact that you have to deal with this area being a hexagon, which I would not do on the test. So if this was a cylinder or a square or something like that, then this would be a really basic problem. Let's do the next set. Let's do AC, or BC rather. All right. So for BC, we're in the shank part of the bolt now. So I would go in the middle of section BC. So here's B and here's C. I'd go in the middle of it and cut the bolt open there and draw that free body diagram. So now the bolt head is there, and I've cut open the bolt, and there is that 35.4 kilonewtons from FA, but now there's also FB pushing back against it, 42.1 kilonewtons. I'm just going to draw it as a single force right in the middle. So in this case, for this piece of our bolt to be in equilibrium, I need more force going to the right. I need a tensile force in here. So 35.4 minus 42.1, or vice versa. I need another 6.7 kilonewtons going to the right to balance this. If I don't have that, then this free body diagram is accelerating, which means the shank part of the bolt is removing itself from the thread part of the bolt, and so it's broken somehow. So I do need this to be in equilibrium. Here the arrow points away from the body that I drew, so that shows that it's in tension, which makes sense. A bolt is in tension when you tighten it down. The bolt is being stretched out. We can do delta, we'll call this BC, this is section BC, equals FBC, LBC, EBC, and ABC. So the force in here is a positive 6,700 newtons. Positive because it's not because it's going to the right, but positive because it is going away from the body and it's in tension. The length of BC is from point B to C, 8.8 centimeters, which we'll need to convert. 1 meter is 100 centimeters. E is the same material, so we can use the same 180 times 10 to the 9th pascals. It has a different area though. Let's see what it tells us about the area. It says, I think that's DS for the diameter of the shank, and we have the diameter of the shank is 13 millimeters. So that's a circle, and we can just do pi diameter squared over 4, and then we'll need to convert, same as last time, because it's in millimeters, it's squared again. So we need to do that. All right, so this one should come out positive, being stretched. And let's see, we have 13 squared times pi divided by 4 divided by 1,000 twice. times a 180 times 10 to the ninth. That's our denominator. 6,700 times 8.8 divided by 100 divided by our denominator. Let's get a bigger number. Positive, remember that was negative. I didn't put a negative sign on there, but that should have been negative. 2.468 times 10 to the negative fifth meters. Let's just check and see if WebWork likes that number. 2.46779, that's what we have. So we do have that correct. Then it asked us to do, you know, the next section, the thread section. And we would do the same thing. We would cut through the middle of here, pretend it's not cut over on either of these, and draw the free body diagram starting from here and going all the way to here. And we would find our internal force, the thread area. So notice it says DT effective. When you have threads, normally what you do is you actually look up the thread area in a chart. But in this case, they're going to have you calculate it as a circle and just say the effective diameter. Because they're threads, then you know there's an outside and an inside diameter. And so they're saying the effective diameter if it were a circle. So we would do basically the exact same thing we just did. The difference would be we'd have a different force and we'd have a different area. And I guess we'd have a different length too. The length of this is C, which is 14.4. So this one, all of this one together to actually finish it, solve the change in length of the entire thing is what it actually asks you to do. That's an A-level question because of the amount of things that you have to do. And the weird hex head thing, which you probably don't know. So this one in its form like this wouldn't show up. You change the head to a cylinder and do a couple of sections like this and add them together to get the overall change in length. That's certainly an average problem. Probably not quite an advanced. You know, I don't even know if I have Centroids listed as one of the A-level things. Let's see. I don't have them listed as there, so it's just an average question. So this one would be average if that head was a circle. And there's 3 sections to add together, and they're each one, you know, some are compression, some are tension. Then it'd be an average level problem. Not tricky, a little time consuming, and plenty of room to make careless mistakes in there, which that's going to be the issue on a axial deformation. They're not particularly hard problems, but there's a lot of room to make some kind of math error in them. All right, let's see if we can find a centroid problem to look at. Let's see, centroids are in, I don't remember which homework they're in. That's more trusses, so they're after that. All right, so this is about as simple as you can get, other than like 2 rectangles together. So this one does have the idea that it is a semicircle. So you do have to go look up. You probably have to look up that centroid. You may not know the centroid for a semicircle, and you have to look it up. Which those are in the references somewhere. I don't know exactly which page the centroids are, but they're in here. I think they might be on this other page. No, there they are right there. So you would have those to reference. So let's see. So that's not work that one. This one would be what I would think of as average centroid question. This is an average centroid question. This one's got a little bit of a trickiness to it. Because of the arc here, the sector actually, this one could be a little bit tricky, and it might even be something I wouldn't ask on an exam just because of that. Let's look at what else we have. Oh, we need to do one of these. We haven't done one of these. So this is the same thing as centroid, but then here the centroids are representing loads, distributed loads. And we need to work one of those, because I don't think we've done one. All right, and there might be one of these somewhere on an exam. One, I don't know. So what's going on here is, most of the time so far we have only dealt with loads represented as an arrow, like a single point load somewhere. But that doesn't accurately describe all the situations you might want to look at. Sometimes instead of applying a force at a single point, you might want to apply a force that's spread out over an area instead of just at a single point, because that does act differently. The material responds differently to being pushed at a single point versus the same amount of force but spread out over an area. That's different. And this is how we show, these are called distributed loads. And this is how you can show the idea that instead of a force that's at a single point, you've got a force that's spread out. And here we've got an oddball selection of shapes to represent this load, but it's an academic problem. So here's how I would deal with this one. I have a quarter circle here. So that's part one. I have a triangle here, part two, sitting on top of a rectangle, part three, and finish it up with a rectangle, part four, or maybe a square. I don't know the dimensions. So the height of these, instead of being a distance, the height represents the magnitude of the force. So you can kind of see these W values are representing the height of these shapes that we've drawn. And they're units like 7 kip per feet. And so what you're thinking of there is you've got some sort of surface, in this case the top of this beam, and instead of putting 100 pounds in a single spot, the load is better represented as, this load that is 10 pounds per foot, and it's spread over 10 feet. So it's a better representation of what's actually going on when you're trying to model this thing, whatever is actually spread out versus a point load. So when you're doing these distributed loads and you're trying to figure out, this is actually asking for, down here at the bottom, the force lumped. So what that means is the picture you have, not this picture, let's get rid of it because it's not really part of this problem. The picture you have is a distributed set of loads, and the answer it's asking for F lumped is if you did take all of these distributed loads and squeeze them down or lump them down to a single point, what would that magnitude be? So basically you just calculate all the area. And then the other thing it asks for is X lumped. So now that I have all of this force that it was originally spread out lumped into a single point, where do I put that to have the same moment effect? And so we'll work through this. So you're basically finding the centroid of a shape. It's just that the shape represents distributed forces. So we can go exactly like we've been doing. I will put, this one doesn't have a x-axis on it or y-axis, so I'm going to put x here and y here. I don't have to worry about the reactions at A and D because I'm not trying to solve for the reactions. I just want to find where would I concentrate this set of distributed loads. Where would I concentrate them into a single point? And what would that magnitude of that single point be? Single point force be? So, whoops, didn't want green. Part 1 is quarter circle. 2 is a little triangle, 3 is a rectangle under the triangle, and 4 is a rectangle off to the side. We calculate each of their area. These will be, what units do we have? Feet, looks like. So the area of this quarter circle, I'm looking at W. All right, so they did actually make it a quarter circle. I was checking that it wasn't some kind of parabola. So its height is W1, so 7 kips per foot, and its base is 7 also, 7 feet. So it is actually a quarter circle and not some parabola or ellipse or piece like that, which would make it significantly more difficult because we'd have to go figure out that centroid, and I don't offhand know that. So the area of a circle would be pi r squared, or pi d squared over 4. In this case, I actually do have the radius r being 7, so I'm going to use pi r squared. Pi times 7 squared, but I have a quarter circle, so I only have a fourth of a whole circle. So the area of this, now this area is not, I wrote feet squared, but the area is not actually feet. If I multiply 7 feet times 7 kips per feet, I actually get kips, right? So it's 38.48. So in other words, this quarter circle is representing a load of 38.48 kips. The triangle is tricky also. The triangle has a height of this point, which is labeled as W3, 5.7, except I only want the height of the triangle, which would be W3 minus W2. So 5.7 minus 3.9. So it actually has a height of just 1.8. And that would be kips per foot, times a base of B, 8.8 feet. But it's a triangle, so divide by 2. So it's actually representing a force of 7.92 kips. And then the rectangle underneath it has a height of W2, 3.9, times B, 8.8, 34.32 kips would be the area. And the rectangle at the end, W3 is 5.7 and C is 7.4. So yes, rectangle, 5.7 times 7.4 is 42.18. These all end up in kips, and the area, the total area, 38.48 plus 7.92 plus 34.32 plus 42.18 is 122.9 kips. That should be the entire lumped load. Let's see if we are correct. Well, they have it in pounds, but 122.9 kips would be the same thing as 122,905 pounds. So we did do that correctly. Then what I would do is I really do treat these as areas, and I would go in and let's maybe do blue, and just mark where the centroid of each one of these would roughly be, just by eye. And measuring from my reference y-axis, I get the x-coordinate, which is in feet, of each one of these. So for a quarter circle, this one, if you don't remember, the centroid for a half circle and a quarter circle is 4r over 3 pi. But that is measured from here. And what we actually want is the distance from here. We have a mirror image of the picture I drew here. So the distance between the centroid and the y-axis for part 1 is actually a minus 4r over 3 pi. So 7 feet minus 4 times 7 is the radius over 3 pi. So 4.029 feet. The triangle is similar. The distance a lot of times that you're given in a chart is that the centroid from the fatter end of the triangle is 1/3 of the base. But I actually want, in my equation or in my chart, my bookkeeping table over here, I actually want this distance is x2. So that's A plus B minus 1/3 of the base. So 7 plus 8.8 minus the base 8.8 over 3. 12.87. I don't know how picky it's going to be. Well, we're just looking. We'll get close enough. 8, 7. The rectangle underneath it is A plus 1/2 of B, because the rectangle of the centroid is just in the center of the rectangle. So 7 plus 4.4, 11.4. And then the last one, the centroid of the W3 rectangle, is A plus B plus 1/2 of C. So 7 plus 8.8 plus 7.4 divided by 2. 19.5. And then finally we do A times X, which will give us kip feet. 38.48 times 4.029. 7.92 times 12.87. 34.32 times 11.4. And 42.18 times 19.5. Then we need to sum all of that together. So 822 plus 391.25 plus 102.32 plus 155.04, 1471.12 kip feet. And then X sub C equals that number, 1471.12 kip feet, divided by the area, which is actually kips. And that will leave us with feet as our answer. So 1471 divided by 122.9. It says 11.97 feet. So what that says is that if I took this weird shape, the quarter circle, the triangle, the two rectangles, combine them into a single point load, I would go roughly here. Let's see, let's do a red one. Let's see, that's 7, and we need to go over basically right here. I would go over that far, which is 11.97 feet, and I would put a single 122.9 kip load at that point, and that would have the same effect as far as a moment goes about point A, or about any point actually. But we use point A more or less. That's how we wrote our table here, because that was where we put the y-axis. And that 122.9 would represent this entire force. So you sometimes you need to do this when you are trying to find external reactions. Let's say I wanted to find dy, the reaction at D over here. Instead of dealing with each one of these distributed loads individually, I could treat them as this one force, write the moment equation about point A, and solve for dy that way. You can't leave them as distributed forces and solve them without calculus. Let's see if we're even right. Dogs are barking at something. 11.97. That's what we got. So we're good on that one. This one is tougher. I would count it. Let's see. It could show up. It's still a little tough for this average question centroid problem. But the average question centroid could be a distributed load. This particular one has so many distributed loads that it takes a while to do. That this one's probably a bit much for that. If this one didn't have the triangle in the middle, or it didn't have the quarter circle on the end, then yeah, I could see this being kind of an average level problem. Still a little tough, but it would be in that range of level. Oh yeah, you will be given the Centroid formulas. Well, you're not given the formulas. What you have are you can use these exam reference 1 and 2 sheets, which are in Moodle. So you can print them out separately, or you can just look at them on your computer screen. It's actually kind of nicer on the computer screen because you can zoom in to them and actually read stuff. Where if you print them out, it's kind of small. So you will have them. Here they are. They're in the exam reference 2 PDF. That's in the reference materials on the introduction part of Moodle. And if I remember, or if somebody will remind me, I will put these also on exam 1 day so it's easier to find. So you have these. And these are copies from the book, the same book that you're using. So you'll have them. Are there any particular things? We've got, 35, 40 minutes. So we can do another problem or another part of a problem or two if there's something particular that you're interested in. I'm going to look and see if I see anything in particular. This design problem at the above average, it's not technically that hard, but this is something similar to, let's see if I can find, it's actually one that we did earlier, maybe in homework 2 even. No, homework 2 is going to be 3D stuff, so it's not homework 2. Maybe homework 3. Sort of like that. It's got to be a better one though. 3D force vector. Yeah, we can look at one of those. There is one on the exam. This is what I'm considering a design problem. Something like this one. So it's in homework 3, problem 4. Because what you're doing is you're not just solving for forces. You do have to solve for forces on parts, but you're using those forces, in this case, to solve for how big does this pin diameter need to be so that it has some set factor of safety. Well, in this case, they don't give you a factor of safety. They just tell you the maximum allowable shear stress on this pin. And so this kind of problem is what I mean for design down here in the above average. So the actual work you do isn't that complicated. It's pretty straightforward, but putting it all together, how does this force try to fracture this pin or whatever it is, and what's my factor of safety need to be? So there's all the little pieces you have to put together. Let's look at the 3D problem. Let's see. 3D is going to be tougher to do just because they're lengthy, but we can get one done. So this one is really, I mean, it's only got 2 forces. That one's probably not. The 3D problem that we have is at the above average level, so it's going to be one of the ones that's a little more than this. Maybe something like this. This is pretty straightforward, except I think this one actually has a little bit of a interesting twist to it, doesn't it? I think it does. Oh shoot, didn't want to do that. I think it does because F3 is along the y-axis. It has no x and z component, just a y component, and so that actually makes this one solvable without having to do simultaneous equations, I believe. Let's find something. Oh, I know. There's one in the optional problems that's probably a good one to look at, if I can figure out the number of it. Hey, well, there's you one of these to work on. And some centroids. This problem has actually been a test problem before. You're not going to have to do one of the centroids by integration. Just looking for a good 3D problem. I think I've actually already worked this one. It is a good one. See if there's something different. Well, this one's at least sort of different. We can work on this one. So, and if you don't remember, the optional one has problems that are test level questions. It's a mix of really straightforward and a little bit more complicated, at least in the sense that it's 3D problems. So you don't get any credit for doing the optional one. You do get extra credit for doing the challenging one, but they are, challenging. So you might look through these optional one for some practice problems. That one, I need all of this on one page. We got to zoom out a little bit. There we go. Try again. All right. All right, so we've got this hot air balloon. Has 3 mooring cables. The net lift of the balloon is 200 pounds, so it's pulling up with a force of 200 pounds. So that does flip our axes around a little bit from what they normally would be. We want to find each of the cable forces. Now this one does simplify us a little bit because it gives us coordinates for the different points. And that's probably, it saves us a little bit of time, but there's a issue with it that we need to look at, because where they're measuring everything from is down on the ground level, and the concurrent part of this balloon and cables is up here at D. And it is way better when you're solving one of these, it's way better if you put your origin at the concurrent location. So that's what I'm going to do. I'm going to put X, well, that's Y, this is X, and Z up here at D. So that will change some of these coordinates. We can't just use the coordinates that they have listed. We can use the X and Y, but the Z is going to be changed. So A, this front cable, X of 20, Y of 28. Z now is from up here down to the plane where the cable is attached, the moor is attached. So it's actually negative 70. B, 18, negative 27, also down at negative 70. This is 0, 0, 0 now. And then this one in the back, negative 26, negative 16, negative 70. Okay. And at that point, we need to find the length. Let's see. This is A, B, C, and D. So the length of AB or AD. To do that, I need my calculator, and it's going to be the square root of 20 squared plus 28 squared plus negative 70 squared. $78. Hey, I wonder if these are all going to come out to be integers. Not A, L, B, D. Oops. Square root of 18 squared plus negative 27 squared plus negative 70 squared. Not integers. 77.16. I don't even know. I assume these are feet. Yeah, these are feet. LCD. Square root of negative 26 squared, negative 16 squared, negative 70 squared. 76.37. Okay. So these are the lengths of the cables, and again, the cables in this case are representing forces in the cables, and what we need the length for is that's going to be the hypotenuse in our equation to calculate cosine equals adjacent side over hypotenuse, and these are the hypotenuse values for any of the cosines that we need. So we need to write in matrix form the summation of forces in the x direction equals 0. We need to write that in matrix form for this. So what I would do is I'm going to have all of the AB coefficients in one column for all three of, we have to write x, y, and z equations. So all of them are going to start with AB, and then we might as well do BC, and then CD. Not AB, I'm doing these all wrong. They all go to D. AD, BD, and CD. And then we'll have our constants, because I didn't draw straight up 200 pounds. The lift from the balloon, but I didn't draw that on there. But that's not going to be in the x direction. It is possible that the known force is not in a coordinate direction, x, y, or z, and it's at some angle. All you do is you break it into the x, y, and z components, and then it can show up in multiple of these equations, these equilibrium equations. So the x component of AD would be AD, whatever the value is, the tension in AD, we'll call it tension in AD, times cosine of the angle between, I'll just write theta x for now, but cosine of theta x, instead of figuring out the actual angle theta and then plugging that into our calculator to get the cosine, we're going to use the definition that cosine is the adjacent over the hypotenuse. So instead of even worrying with the angle, we're just going to say, oh, well, it's the adjacent side, which for AD is 20, x, it has a x coordinate of 20, and the hypotenuse of 78. See, I saw a chat. Let's see. It's probably just hidden right now. The question is, are you going to actually take the exam in Moodle during class time? Yeah, I probably just have it hidden so you can't see it yet. But it will be in Moodle. And you'll log in. I'll send you a Zoom link, and you will log in to that Zoom link, log into Moodle. The exam will be there, and you'll take the exam in Moodle. And then you'll upload scans, pictures, whatever you have of your written work just after you do the exam. After you finished all the exam, you'll upload it. So you probably can't see it yet just because I have it hidden. I don't want somebody accidentally getting in there too early. So TBD times the x component of BD, which is 18, over the hypotenuse of BD, 77.16. So I hope the point of this, I hope you're getting, is that this number, 20 over 78, that is the cosine of theta x for angle, or for cable AD. Plus tension in CD times the x component of CD is negative 26, and the hypotenuse is 76.37, equals, there is no x component of the, what you call it, force from the cable, force from the balloon. And then we write y. TAD, again, I'm doing all the ADs first. So the y component of AD is 28, same hypotenuse. BD times negative 27 over 77.16. CD times negative 16, 76.37. And there is no y component of the cable force from the balloon. TAD times these are all 70, right? Negative 70. So it's not good to, whoops, not F, I'm doing T. It's not good to just find patterns in these things and just always do the pattern, but there are clear patterns in this method of doing it. These forces equal 200 pounds. Or if you write it the other way where the equation equals 0, then you would have minus 200 pounds equals 0, and then you move it over to the other side and it equals 200. Now I will say one thing here that I have kind of skipped over, or not skipped over, but I have mentally just inverted. I actually worked this problem a little bit backwards now that I'm looking at it, in that the 200 pounds is actually in my positive z direction, but all of these others are in my negative z. Okay, that's fine. I did put my negative z values in there, so that's okay. So this would actually equal a negative 200 here, because if you wrote your equation, you know, summation of forces in the z direction equals 0, I have all of these negatives plus 200 pounds because it is going upwards in the positive z direction. And when I move that to the other side of the equal sign, that becomes a negative 200. So it actually equals negative 200 pounds. These are 0 pounds. Now, at that point, you'll need to get this into some sort of simultaneous equation solver. And it's okay, whatever calculator, you're not going to have MathCAD on the exam, but whatever calculator you're using, well, I won't say any, most any scientific calculator will at least let you put these in as matrices and solve them that way. And most of this style calculator are going to have a equation solver where you're doing the same thing. You're putting the coefficients in, and you're putting in the residuals, the zeros and the 200s, and it's just doing the matrices behind the scenes, and you just don't see it. It doesn't look like a matrix. Either way, you need to be able to solve these equations somehow. So I'm going to put this into the equation solver, simultaneous, 3 unknowns, and so you can kind of see, maybe you can see it just in this particular one, it sets it up to where it's a matrix that looks a whole lot like what I've got on the screen. And you just put the coefficient, you don't put the AD and BD, you just put the coefficients in. So 20 over 78, 18 over 77.16, negative 26. Plenty of room for error in putting all these things in, right? 0 for the residual. 28 divided by 78, negative, oh, I should have written clearer, 27 divided by 77.16, negative 16 over 76.37, another 0, negative 70 over 78, negative 70 over 77.16, negative 70 over 76.37, and negative 200. And then there's a little solve button. We get a bunch of numbers. They all came out positive, which is good because I drew these as tensile forces. They're going away from the body. The body, I didn't draw the balloon or anything. You know, you can imagine the little balloon box is sitting right here. But that means that they're all in tension, which these are cables. Cables, as far as we're concerned, can only support tensile loads. You know, a really big cable can have a compressive load on it, but these are made to just be tension. I drew them in tension, and I got, let's write down what I got. I got this as my answer. I got a matrix as my answer, the way that this works. And I got 90.347, 36.833, and 93.284. Now, my calculator just says X, Y, and Z, but this is the matrix TAD, TBD, and TCD. Now, let's see if any of those numbers are right. So that's always a scary part. Yeah, those look right. 90, 36, and 93. That's what we got. So nothing terribly complicated, but little places to go wrong. Lots of, putting these coefficients in right, not dropping a negative sign somewhere. Either figuring out or being given the coordinates of the points, A, B, and C in this case, or you might be given a picture and you've got, this kind of thing where you've got to figure out the y components and the x components based on some kind of dimensions you're drawn on the diagram. And so that's the same thing. It just means that you have to go in and figure out the values. So can you explain why the z coordinates are negative 70? Yeah. This is a thing that I chose. So when working these 3D problems, for me, and probably for most people, but not necessarily everyone, it is simpler to have your origin for your coordinate system at the same point that's all the concurrent forces meet. And so this one's drawn with the origin down on the ground, but the intersection point of all the forces is up at point D. And so all of these, they gave me all of this, but they all reference this origin down at the bottom. So if I were measuring from here, then point C's coordinates would be negative 26, negative 16, 0, and point D's coordinates would be 0, 0, 70. But I don't want to measure from down there because it makes the angle calculation. Now I don't have cosines that are nice and easy to work with. And so what I did is, instead of using the coordinate system down on the ground, I moved it up to here. And when I did that, now point D's coordinate system is not 70, it's 0, 0, 0, but that meant that I raised this z coordinate, or well, actually I raised the coordinate system, which made this a negative 70. Hopefully that makes some better sense. Some of the problems that you work, they have the origin already labeled at the intersection of all of the forces. This one didn't. And it is just so much easier for doing this method with the cosines if the origin is at the point of the concurrent system, the intersection point of all these forces. And so when I raise the axis up, that's why all of the A, B, and C's got negative z components now. And D got a 0 z component because I made it the origin. All right. We have a few minutes left. I don't know that I have time to work through an entire thing. Maybe I can answer some questions if you have them. But let me just look in here. We've covered the main types of things. We did not go back and specifically talk about axial stress or shear stress separately. There will be problems where you do axial stress. So if you go back into homework, which one? Maybe homework 3? Let's see. Yeah, these type problems. Working a problem like this will give you plenty of practice with shear stress, axial stress or normal stress, tear out stress, which is a shear stress. If you can do this problem, which is homework 3, problem 3, then you are pretty well set on the axial and shear stress problems. It won't be this same problem, but it's the same idea with calculating axial stress or shear stress, something like that. All right, I didn't see any new questions pop up, so I'm going to assume we're good for now. You can still email or send questions over to Discord. I've gotten a little more email questions lately, so that's good. Test is on Thursday. I will send a little bit more detail on what you're going to do, but basically you'll have a Zoom link on Moodle and you'll have an exam link on Moodle, and you'll log into Zoom, camera, but no sound. You don't need sound. And then you will take the exam, write out your work the best you can, take a picture, or if you have a scanner, then scan your work. There are plenty of scanners that basically take a picture and turn your picture into a PDF, and you'll upload those as your written work. Right after you finish the exam, you'll have another 10-15 minutes to upload your written work after you finish the exam. The exam will score automatically because it's in Moodle, but I do have to go in and adjust things, because it doesn't do any kind of partial credit correctly, and so there will be a period of me adjusting the grade after it gives you a grade. It never drops down lower, so Moodle gives you like your rock bottom grade, and then I go in and assign any partial credit or corrections or anything like that. All right, I will see you on Wednesday. Wednesday, we are not doing exam material. We'll actually start on exam 2 material on Wednesday. But I can still answer a few questions about exam 1 on Wednesday also. All right, see y'all on Wednesday.